Conversion rates meet statistical distributions, a primer for the digital analyst. My name's Tim Wilson. I'm a senior director of analytics at Search Discovery and also a co-host of the Digital Analytics Power Hour podcast. And what we're going to do in this little video is dive into some of the concepts behind conversion rates, which actually are an aggregation of conversions. And conversions are, it turns out, we get fancy with the terminology, a Bernoulli metric, and a combination of Bernoulli metrics wind up in a binomial distribution. And things get really, to me, I think, confusing very quickly. But we're going to walk through sort of how to maybe unwind that confusion, get some understanding of how these two things come together. It's really important if you're doing, A/B or multivariate testing to really have some intuition about this. But even if you're just working with traditional web analytics data and looking at, hey, conversion rate for the last month, I think it's actually useful to sort of understand this stuff. I was a little confused about it. I thought I had intuition on a few different fronts. When I put them together, I realized maybe things didn't quite make sense. So we'll walk through that, and then hopefully we'll emerge on the other end with a good understanding of how this stuff comes together and maybe actually why it matters, I hope. So let's dive in. So I'll say up front, kind of apologies to Randall Monroe. This entire presentation has an XKCD theme, and we're just going to run with it. It is actually built with R. At the very, very end of the presentation, if you're curious, I go into a little bit of the details of how this was built. I actually did use simulated data in this presentation to sort of provide some of that intuition. So stick around till the very end if you're curious about that. So start off with, we have a normal distribution, right? We're all familiar with this. If we've had more than about 12 seconds of statistics ever, we've seen a normal distribution. And we sort of get that when we have an A/B test, we understand intuitively that we have two distributions and that we're kind of thinking about the overlap of those distributions when it comes to things like power and confidence and one-tailed versus two-tailed. And I would say we even go a little bit farther, that we recognize that this distribution is kind of an underlying unknowable population distribution, right? And that we are really only observing one value from that distribution, and we don't really know what the underlying distribution is. And that's where kind of some of the risk of getting false positives or false negatives come in, is that we don't know where our observation is falling within those population distributions. But we're going to get a little bit more precise because actually some of that's not particularly accurate. So let's think about conversion rate just for a minute. Let's go back to our single distribution. And if we think about conversion rate, we start actually realizing that how does that become a distribution? What does it really mean to have a conversion rate or the distribution of a population of conversion rates? Well, for one thing, if we think about it, that conversion rate is actually taking a whole bunch of conversions or not conversions, is taking the total orders or total conversions and dividing that by the total visits, which is actually the same math as calculating a mean. So if we actually had all the data, don't we actually have the population mean? Our conversion rate is the population mean? That's kind of where I was, and that's not really particularly accurate. So if you were saying, yeah, this totally makes sense, that's not exactly how we get to a distribution that we actually work with. So what we're going to do is we're going to go through some thought experiments where we pretend we have an entire population, and we're going to go do various iterations of kind of pulling samples from that population. But let's start with our population and see how we can get to a distribution. So we never actually have the entire population. We'll actually get to a little bit of a discussion of what is the population in a bit. We don't actually know the population, but we're going to use it for this thought experiment. It's going to be a relatively small population. We're going to say that our total population is 1 million total visits, or total sessions or observations, whatever. It could be visitors. And we're going to say that we have 30,000 orders across those 1 million total visits, which means we have a conversion rate of 3%, right? 30,000 divided by 1 million is 3%. Pretty straightforward. That's our conversion rate. So how does that 3% become a distribution? Well, one way to look at this is we had 1 million visits. That's really 1 million observations. And really, in the underlying data table, we'd have a row for each one of those observations. And each one would be flagged. This is where converted is a binomial metric. It's either they did not order or they did order. And that could be a 0 or a 1. It could be a true or a false. Here it's shown as did not order or ordered. If you're looking at Google Analytics data going into BigQuery, this is basically what your table looks like. Obviously, I've eliminated a bunch of columns, and I've done a little transformation to get this one column that says converted or not. with Adobe's data feed, the hit level data, some level of sessionization, you can get to the same sort of thing. That's kind of the raw data that we work with. Now in this case, we only have a 3% conversion rate, so most of our rows are going to be flagged as did not convert, and a handful are going to be 3% are going to be flagged as did convert. So hopefully that's clear in what the data set is. So how can I actually make this into a bar chart? Well, or into a distribution. I could just count up the total number of observations that were did not order and the total that ordered, and it's actually not that helpful. I have one bar that's 970,000 observations in it. That's my did not order, and 30,000 that did order. So that's not really marching me towards anything that looks like a normal distribution. So we have to do something different. And that's what we're gonna do is start sampling. We're gonna introduce this concept of pulling samples. So it turns out that if we actually have all of the data, an entire population, we don't really have a distribution. What we have is the actual conversion rate, the overall mean. And separately, if we drill down into it, we have a bunch of observations that have binary or dichotomous outcomes, basically convert or did not convert. But let's look instead at samples from our population. And what we're going to do is we're going to say, let's just pull an arbitrary 1,000 visits at random, 1,000 observations, and calculate the conversion rate for those 1,000 visits. Well, in this case, it got us to 3.2%, which is close to 3%. So that sort of makes some intuitive sense. I just pulled a sample. It somewhat reflects the population. I did it again. I put those 1,000 back, pulled another 1,000. I got 2.3%. It's a little farther off, but again, it's kind of in the ballpark of 3%. Do it again, 1.9%. That's a little alarming because that's a full percent off of what I know the truth is. But I can do this again and again and again. And every time that I put my 1,000 observations back and pull another 1,000 at random, I'm going to get a different conversion rate. So let's look at saying maybe we do that 100 times. And that gives us a table that has 100 rows. Each one has 1,000 is summarizing 1,000 observations where we've calculated a conversion rate. Well, now this is something, if we take that conversion rate column, I can start to actually represent as a histogram and bucket those and maybe get to something that looks like a distribution. And here I've got buckets or bins of 0.2% each, and I've got something that's starting to look like a distribution, although it's not a very smooth distribution. So how can I make it smoother? Well, I could pull 5,000 samples of 1,000 visits each, and each time I'm pulling 1,000 visits, calculating the conversion rate, recording it, and putting that back into the whole population of 1 million. And if I do that, I start to get something that starts to look like a much smoother histogram, starting to look like a normal distribution. Well, rather than representing it as a histogram, I can actually represent it as a density plot. It's the same data, but now I've got kind of a smooth curve that's representing the data. And again, if we go back, this histogram, very, very similar. You can see that it's kind of smoothed out. That's what my density plot is. So let's take a recap of what we did there. We pulled multiple samples. We pulled 5,000 in our second from our population. We used the mean of each sample as its own observation, the sample mean, and then we created a distribution of those sample means, right? So in reality, we don't get multiple samples. We just get one. We get the one set of data that we pulled. So we get this one sample. We don't know what the population conversion rate is. We don't know what the distribution actually is. We never actually see that. We just get this one point, and we don't really know where it falls in this larger context. So what is that sample? Well, now we need to maybe step back a little bit and say, what is the population? And I've over time, I've managed to ask various people, hey, what is the population when we're talking about digital analytics data? And people are like, well, that's obvious. And then we wind up in a discussion because it really depends a little bit on what we're trying to do. If we think about our data is non-stationary. It exists over time. There's past data, there's the present, the moment in time, and there's future data. And what is our population? Well, if you think about the way that often from a web analytics perspective we look at it, we say, well, sampling is bad. We have all the data. And in that way, we're kind of inherently saying we have the population is all of the past data up till now. Maybe that's our population, but that's kind of just the historical data. Maybe it's like, well, we want it for all time. We want our population is the past, the present, and the future, knowing that we don't have the future data, we don't have any of that population, but that's what we care the most about. Or maybe really, especially in the context of A/B testing, but even when just doing standard reporting and analysis of historical data, we really do care about the future. How do we make the future different? How do we impact the future? That's our population. So what's our sample? Well, we can't pull a sample from a population where none of the data exists. So we wind up pulling a sample, and this is absolutely the case in A/B or multivariate testing, is that we're pulling our sample as kind of a sample time frame. Now here's kind of a key thing about this, is that maybe we recognize that this is imperfect. And it's imperfect because this data is non-stationary, the environment that we're working in is changing. The farther we go back in time, the more different the whole environment is. The way consumer behavior was different, the way our site, the way our competitors were acting, of different campaigns that we were running. The farther in the past we go, the less like today that data is. And we can project that forward as well. The whole world is not, the universe is not staying fixed and constant. The farther into the future we go, the more things will get different. So our sample is really just kind of most indicative of right now and the near future. But that's kind of the best we can do. Let's think about having our A/B testing. In that, we're kind of envisioning two parallel universes. And we want to know the conversion rate for both universes, really just for the future. But we pull samples in the recent past. And the reality is that B universe didn't really even exist until we probably started the test. So this is a little bit of a misrepresentation. But conceptually, we think of it as saying we want to have these two parallel universes, and we're pulling samples from these two different populations. So hopefully it's clear these samples are not random samples from the population. In our exercise earlier with the 1,000,000 visits, we just pulled 1,000 at random. But here, these are not random samples from the population. So really, we're making a big assumption that these samples in time are sufficiently representative of the entire population. We're pulling a sample from the recent past and trying to use that to say it's representative from a population that is just the future. That's really just the way things go. There's nothing we can really do about it. So let's go back to our population mean and our sample distributions. Or to be a little bit more accurate, they're actually distributions of sample means. And we don't actually know what the population conversion rates are, right? We don't really know what A reality and B reality or those distribution of sample means are. Really, all we have are the two observed values, A observed and B observed, over the period that we were running the test. So how do we actually know what the truth is, what the true conversion rate is? Well, we don't. So let's think about it this way. We've been looking at this scenario and said this happens to be the observed A and the observed B. And say that we ran a test over the last 2 weeks. Well, what if we happened to have run the test 2 weeks earlier, just because that's when it was available and that's when it could be slotted into the roadmap? Well, we could have gotten a different observed A and observed B. What if we'd run it a month earlier? Well, we might have gotten a B that was actually less than A, all within those distributions. That's just saying we ran the test at a different time. That's not even really taking into account the fact that, again, this is non-stationary data. Our population is probably kind of moving around a little bit as it is, and we're kind of just saying for the sake of the thought experiment, and just because we have to, we can't really do a whole lot about it, we have to say that we're going to somewhat pretend that A reality and B reality are actually fixed. But we sort of know that it's non-stationary data. The farther into the future we're trying to go, the more different things will actually be. But they have those two competing things that both make this data somewhat noisy. We just have two data points. And what we have to do is estimate a range within which the true conversion rate falls. We're not estimating the true conversion rate. We're estimating how close it is we expect that we are to the true conversion rate. We just don't really know in which direction we're within that range or whether we're right on top of it. So we use what we do know to estimate how close to the true mean each sample is, the true conversion rate each sample actually is. So let's go back to our distribution of sample means. And again, we're going to pretend that we know that the reality, the truth of the population is 3%, and this is our population that we're working with that we created of 1,000,000 visits, and then we've got our distribution of sample means below that. Now this, I've changed the y-axis here a bit, and the reason why will become apparent here in a minute. But we basically have what we were working with all along. So let's pull 10 samples of 1,000 visits each and see where they fall on this distribution. So, and we can see they're kind of scattered all over the place, but these are 10 different samples. And in reality, I'm only going to pull one, but we're going to pull 10 to start to get some intuition here. And in this case, I've actually added some indication of the variability of that data. It turns out if I know the population mean, which I never really know, and I know the number of observations I'm making, 1,000 observations, 1,000 visits, I can actually calculate the standard deviation around which that falls. So this makes sense that while these are fairly spread out, they still are falling underneath my distribution curve as I'd expect. But what if instead of pulling 10 samples with 1,000 visits in each, I pulled 10 samples with 10,000 visits in each? Well, those look a little bit different. What's going on with that? And maybe intuitively this makes some sense. Well, if I look at them together, I can see that the second, those are the red ones, are the 10,000 visits, and they're much more clustered around the true mean. That's because they're really a different distribution. If I calculate my standard deviation using 10,000 visits around my true mean of 3%, I get a much tighter, much narrower sort of distribution that's occurring. Aha! So, what does that mean? It means the larger our sample size, the more likely the mean is close-ish to the true mean. There's still risk, we're still going to be out on the tails. So let's consider an A/B test just one more time. And pretend that we know the truth, and let's say that our control, or that this population is 3% for A and 3.5% for B. Maybe you're seeing where this is going. If I pull 1,000 visit samples, then this is what my distributions will look like. There's a ton of overlap. There's a very good chance that I'm going to get observed sample means that maybe aren't going to really reflect which one of these is actually working better. If I did 10,000 visit samples, then these are what my distributions look like. There's still the risk of a false positive or a false negative from the overlap, but it's much, much lower. And that's why basically the larger our sample size, the smaller of a change we can detect between a test and a control. We never really know what the true conversion rate really is, but this gets us a lot closer. Okay, so let's wrap this up. First thing we started with was that conversions are basically a binary metric. They're just a yes or a no. A visit converted or it didn't. The way that we actually get to a distribution is that we're actually pulling sample means. We're pulling a bunch of those observations, maybe for the last 2 weeks or the last week or the last month, and we're calculating a conversion rate. And that is actually how we start to get to a distribution. A distribution is a distribution of those sample means. The larger our sample, the more visits, the more observations we're pulling, the more likely we are going to be pulling a sample that's actually close to the truth or to reality. But at the end of the day, nothing is absolutely certain. We never really know what the truth is. And there's a lot of messiness going on with our actual truth because we touched on the fact that we're working with data over time or non-stationary data, which means that we really don't have a static a population that we're working with. There really is no reality or truth for a population that is varying over time. So I do have to thank a few people really quickly. Matt Gershoff, who is always sort of pushing for deeper understanding, as well as encouraging simulations. And there were simulations that were running this data. I didn't make up those dots and put them. I actually generated data and pulled it. Chad Sanderson doesn't even really know he's helped out. He's now at Sephora, used to be at Subway, but actually shared a ton of kind of links and thoughts. Georgie Georgiev from analyticstoolkit.com has written some great content on trying to provide some intuition around these things. And then finally, kind of my co-conspirator, Kelly Wortham, co-worker at Search Discovery, who does a lot on optimization, is kind of on this shared journey with me to try to provide better intuition and explanation out to the community. So if you care about how this was built, it was built using R. This presentation, I used R Markdown, which is super, super powerful. I used Zeringen, which is actual kind of a way to make some better slides using R Markdown. And then I used the package called XKCD from R, kind of battled that a bit. It's available on CRAN to pull this together. with that, hopefully this has been useful. If you see something that you think I missed horribly on, or if you have further questions, I'm easy to reach and via email or via Twitter or the Measure Slack or just about anywhere. Thanks.